Okay, we're going to continue on here, chapter 10, I believe. And obviously in chapter 10, last time we talked about energy. Remember that there are some common units of energy that we use a lot. Again, joules and kilojoules are probably the most common units of energy that you'll come across. The relationship, that's the kilo relationship, which is 1,000. So there's 1,000 joules in a kilojoule is a very common one. I would say probably a little less common, but still used is calories. And again, that's lowercase c. And kilocalories is also used. And that's still the same sort of relationship. That's 1,000 of the little calories equals 1 kilocalorie. We talked about energy and sort of the flow of energy. Remember that we have a law of conservation of energy, which says we don't create nor destroy energy, but it can be transformed from one place to the next or one form to the next. And when we talk about sort of the flow of energy, we talked about sort of our system and again, our surroundings. Remember that, as energy flows from one place to the next, whichever way it's going, we will always get sort of that equal amount of energy. And so, for example, whatever, say, the system will lose in terms of energy would be the amount of energy that the surroundings would gain, and vice versa. Whatever, for example, the surroundings may lose in energy, that system should gain it. It's really those two processes that we talked about, which are exothermic processes. And exothermic, meaning obviously that energy is released, and endothermic processes, which mean that basically energy is absorbed. The way that these two processes are sort of related, are sort of signaled in calculations is typically if you do any type of energy calculation that's an exothermic process, you will get a negative number. And any type of endothermic process will yield you usually a positive number. Now, we talked about some important sort of units or ways that we express energy in experiments or reactions. We also looked at in relationship to exothermic and endothermic energy diagrams. And again, this is our reactants, this is our products. That hill, again, is the activation energy has to climb. That is a exothermic diagram, as the reactants are higher in energy than our products. We also had an endothermic sort of diagram, and that looks a little bit different. We look something like this. Reactants are actually lower in energy than products. And that, again, it would be our activation energy there. And that would be an endothermic reaction. So delta H, which is the change in enthalpy, is a probably the most common way that you sort of see exothermic or endothermic sort of given to you in equations. You could calculate, as we did in some examples, the delta H of the reaction by taking all the delta H values of your products minus the delta H value of your reactants. We did a couple examples there where you go to a table basically and look up those values. Remember that you do need to multiply it by the coefficient in the equation to each of those values when you do that. Again, if you get a delta H that is negative, that's going to be an exothermic process. You get a delta H that is positive, it will be an endothermic. And that's because if we sort of look at our diagrams here, my superly small drawn diagrams here. If you take the difference in the energy between, say, the reactants and the products here, and again, that's going to be our products minus our reactants. Here, the products are actually a smaller number because it's lower in energy than our reactants, which is a larger number, and that's how you're going to get a negative value for delta H. That is opposite here in our endothermic. The difference between the energy of your reactants and your products would be your delta H. In this case, when we would do that calculation of products minus reactants, Our products are higher in energy, which means it's going to be a larger number minus a smaller number for our reactants, and that's going to yield you a positive number. So we use delta H a lot to know whether or not, for example, a reaction is exothermic or endothermic. And very commonly, when you're given an equation, that is how it's usually displayed to you. They'll just simply at the end of it give you the delta H value. It'll either be positive or negative in terms of its number. The number really doesn't matter all that much in terms of whether it's exothermic or endothermic. It really is just the sign, again, that's important in terms of is it exothermic or endothermic. We also talked about when we talk about energy and exothermic and endothermic, the placement of it or what we think about in terms of energy is different. Energy is a product if it's an exothermic type of reaction, like it's being given off, and energy would be a reactant if it is a endothermic process, like it is being sort of absorbed or added to your reactants in that case. I would say probably most of the chemistry levels that you would take, including this class, and probably on, they very rarely, oftentimes, will kind of put the numbers into the actual equations. Again, more so, you'll just be given that delta H values more commonly how you'll see it. Sometimes, like in health major type chemistry classes, they oftentimes will put the numbers like into the equations. Another important way that we look at energy is what we were finished up on last time, which is specific heat capacity. And specific heat capacity has units of either joules per gram per degree Celsius or calories per gram per degree Celsius. And it is the amount of heat or energy that's required to change 1 gram of a substance by 1 degree Celsius. That's pretty much, bless you, what the units are. That's the amount of energy you need to raise 1 gram of a substance by 1 degree Celsius is basically what all those units represent. Now, a number that you definitely should know, obviously, is the specific heat of liquid water. And I believe they want you to know that value, which is basically it is 4.184 joules per gram per degree Celsius, or it is 1 calorie per gram per degree Celsius, and this would be liquid water. So those are numbers that you, again, do need to know, as we talked about. That is also, by the way, the conversion that you also should know that we talked about between calories and joules. There are 4.184 joules in 1 calorie. So if you remember that conversion, you'll know the specific heat of water basically is the same number. Remember that, as we talked about, that if you have a large specific heat capacity, that means that it's going to take a lot more energy to see a 1 degree temperature change in a particular substance. If you have a much smaller specific heat capacity, you don't have to put as much energy in there to see a change in that temperature. There is an equation that goes with it, which Q is equal to ms delta T. That is our heat, our energy. And the common units of this guy is either joules or calories. M is mass, which the units are grams. S is the specific heat capacity that we just talked about. And it has either that unit, obviously, or that unit. And the change in temperature will actually have units of degrees Celsius. So as I mentioned last time, it's probably one of the few sort of formulas in chemistry that you come across is you actually do leave the temperature in Celsius. You don't convert it to Kelvin. But more importantly, you want to always, when you do the change in temperature, make sure you take the final temperature minus the initial temperature. Initial and final there. And that's really important because that is really the only part of this formula that will decide whether or not you end up with a positive number or a negative number when you do your final minus your initial. So the idea here is if you calculate Q and you do get a negative value, that is a exothermic process. If you calculate Q and you get a positive value, that's going to be an endothermic process. So that's, again, another way that you could kind of determine that. If the S here, as I mentioned before, sometimes people will use S, sometimes people will use C, and sometimes people will use SH for specific heat capacity. I personally use S most of the time, but there are some other symbols or letters that sometimes books and stuff will use for that particular one. Any questions on any of that there? All right, so we did an example last time and finished up on, so I think we are on this example. So why don't you give this one a go? We have 294 joules of energy is transferred to 10 grams of silver that's at 25 degrees. What will be the final temperature if the specific heat capacity of silver is 0.24? So see what you come up with. Okay, so let's take a look. Again, obviously, we're using our specific heat equation here. In this question, we have our heat, which is Q, so that is 294 joules. Obviously, that is our mass of 10 grams. We have an initial temperature here of 25 degrees Celsius. We are looking for a final temperature. And lastly, we have our specific heat capacity here. So we have everything we need here to actually solve for the change in temperature. So that's what I'm going to do basically first. My change in temperature, we're going to basically divide this to the other side. Will give us Q divided by M times S. Putting in my numbers here, I got 294 joules divided by my mass, which is 10 grams. And my specific heat capacity here of 0.24 joules per gram per degree Celsius. Unit-wise, joules will cancel, grams will cancel, the degree Celsius will flip to the top when we divide, and that's going to give us here a change in temperature, right, of 122.5 degrees Celsius at this particular point. That, again, is not the answer since we're looking for the final temperature. And that's where it's important that you remember the change of temperature is the final minus the initial. That means that we basically got 122.5 degrees Celsius equals our final temperature minus our initial. Once again, we're going to actually add that or to the other side, basically. So we want to make sure that we add in this case. So that will get us a plus 25, which does make sense since we should end up at a higher temperature as it is absorbing that energy. So that should see the temperature start to rise. Ends up with a 147.5 degrees Celsius. So now we want to think about maybe significant figures. So if we kind of, or we should be thinking about significant figures as being going through. The first calculation you do is multiply and dividing. So that is sig fig. So that is 3, right? That is 3. And that is 2, which means technically speaking, this first answer should be to about there, right? Which is like a 120, which should be like a whole number, basically, in this case. So that's basically what we had going on over here. We basically had, technically speaking, a whole number plus a whole number, which means my answer really should be a whole number in this case, as we did adding at the end. And maybe about a 148 degrees Celsius is probably the correctly rounded one in this case. Now, if you went strictly rounding here, you would have ended up with 120 degrees Celsius. Then you would add in, you would end up with 145 degrees Celsius at that point. There is a little bit of difference there. Again, we probably want to hold off the rounding until the very end, but we do want to kind of keep track of everything so we don't have such a little rounding error, for example, in the degrees temperature here. Any questions on that? Obviously, 148 is much closer to 147.5, which is probably the correct sort of answer than with using that rounded number that got you to like 145. Any questions on that there? Okay. So another really important aspect of sort of this heat transfer is what we talked about, that if somebody loses a certain amount of energy, somebody will gain basically the exact same amount of energy. The only difference is really the sign. For somebody that is going through sort of a exothermic process, their energy value will be a negative. And for somebody really going through an endothermic process, their value for energy will be positive. The actual number will be the same. It's just the difference in sign. And we see that a lot with specific heat. And so, for example, like we're going to do today, if you had, say, some water here, and let's just say you had, I don't know, we'll go with 125 grams of water. And let's say that the initial temperature of the water was 25 degrees Celsius. And you take a piece of metal, like over here, a big piece of metal, I guess. All right. So say we had a mass of this metal of, I don't know, we'll go with 115 grams. And let's just say that we heated this metal up to like 99 degrees Celsius. So if we take this metal and we heat it up to 99 degrees Celsius, and then we send it for a swim into our water, what we see in terms of the water is it will increase perhaps the temperature. Let's just say it gets it up to 28.5 degrees Celsius, right? Now, what we do know is in this case, between the water and the metal, which one's an exothermic type situation happening? Which one? It is the metal, right? So heat, as we talked about, flows from the hotter object, right, to the colder object. So clearly our water at 25 degrees is colder than our metal that started at 99. So what we're going to see is the metal is going to release, right, all of its heat basically to the water in this particular case. At some point, because the metal is swimming in the water and can't find its way out, the final temperature of the metal will end up being what? Should end up being the exact same temperature as the water. It'll eventually come to equilibrium in it because it's sitting basically in it, right? So as it releases all its energy, it will eventually come to rest at the same temperature as the water finally rested as well. That's kind of like the little cooler picture we saw last time where we had 90 on one side, I think 10 degrees on the other side, and they both kind of came down to basically the same temperature as they were in basically the same water. So by knowing the final temperature of the water, we will also know in this case the final temperature of the metal, which in this case would be 28.5 in my made up example. So a very common experiment like you're going to do today, you could just use some coffee cups and a thermometer basically, and you can monitor the temperature change basically of water. And a lot of times the reactions, we do this because we also know for water, right? We also know the specific heat capacity of water is 4.184 joules per gram per degree Celsius. So if we wanted to know something like what is the specific heat capacity of the metal, for example, we could do this experiment, and really by the change of what's happening in the water, we could then figure out what's happening with the metal. So let's see what we could do here. So if we think about the water aspect of it, we can use our specific heat equation, Q equals ms delta T. And we do have our mass. We obviously have our temperatures and our specific heat capacity, which means for the water, we have everything we need basically to plug it into here. So we could do that, and we'll go 125 grams. We'll go with our 4.184 joules per gram per degree Celsius. Again, we're going to take our final temperature in this case, which is 28.5 minus 25 degrees Celsius. That's going to get us here. That's going to give us something like, what is 1830.5. The units here, grams, degrees Celsius are going to cancel. These are going to be joules. Now let's talk a little bit about sig fig so we again keep track of where we should really end up. I got 3 significant figures here. I got 4 significant figures here. When I subtract that, I get 3.5, which is two significant figures, right? So technically speaking, my answer should end up right about there, right? That is technically where we should lay up our energy value. So you would technically round this to 1800 if you were going to give the answer for obviously the energy of the water, right? So this number, though, does represent the energy of the water gained, right? And we see that it is an endothermic process for the water, as we ended up with a positive value, right? And that makes sense. We also know that all the energy that that water picked up came from what thing? All the energy that the water picked up came from the metal, right? It is the only thing that basically supplies energy to the system there. So what that also tells you is a really important relationship when you do something like this. For example, Q of the metal will equal minus Q of the water. So whatever amount of energy that the water absorbed would be the same amount of energy that was released by the metal. So we can now figure out actually the Q of the metal should be, in this case, negative 1830.5 joules. Once again, it is the exact same number, but the sign is different to indicate for the metal, like we know, it is a exothermic process, right? Is again releasing that energy, so we do get a negative value for Q. Any questions on that? So why is that helpful? If we now think about our metal and use our specific heat equation for our metal, we now know the Q of the metal, we know the mass of the metal, and we also can figure out the change in temperature of the metal. That will allow us to solve for S. And S is found by dividing both of these guys to the other side, right? So we're going to divide those guys to the other side. That will give us S is equal to Q of the metal divided by M delta T for the metal in this case. So if we put this in, we're going to go with, again, the negative value of 1830.5 joules. And once again, on say why the negative is important there. Our mass here for our metal was 115 grams. And now, once again, when we do the change in temperature for the metal, it is final minus initial. So for the metal, the final temperature is 28.5 minus 99. By the way, when I do this calculation here, I'm going to get what type of number? I'm going to get a negative number, which is important with this negative number to make this into a positive number that it should be. So again, that is how we kind of get back to a positive number by taking final minus initial and obviously having that negative for the energy of the metal. Any questions on that there? All right, so let's punch these some numbers in here. So we'll do that there. So we're going to take our 1830.5. We'll divide it by our 115. We'll also divide it by, looks like 70.5 is what you get in terms of the difference on the bottom there. And we will end up with 0.22578786 joules per gram per degree Celsius, as none of the units cancel. We now have to look at significant figures, right? So we know that technically speaking, the top guy should have 2, right? We do know that this guy should have 3. And when we subtract our temperature, we ended up with 70 point something, which is also 3 sig figs. That means that my final answer here should have how many significant figures? Should have 2, based off of really our original energy value. And that means that we really should go there. And we also should round up. So that should give us something like 0.23 joules per gram per degree Celsius. Any questions on that calculation there? This is a really, really common sort of way that you can figure out pretty much the energy for a particular reaction, what's happening. Frankly, to do this, it is like super simple, like you're going to do today. You just need a couple of styrofoam coffee cups and a thermometer, and you pretty much can do any of these type of calculations. You can figure out the energy of like the heat transferred from a metal you actually do chemical reactions and mix them together. And because most chemical reactions or most solutions are water-based, you can still just assume that it's basically water in there, and you can use the specific heat capacity of water and basically just figure out the energy that is changing. So this relationship, which is this idea that when you transfer one object to another, there is no energy loss. It should equal zero, and it's the sum of those two objects. Now, the important part here is you do need a negative somewhere, yeah? So for example, if we took all these guys to the other side, we would get basically this negative relationship here, again, of our, say, metal would equal our water. So again, it's really important when you do this that you do incorporate that negative on one of them. It really doesn't matter, but you just got to have that negative in there on one, or either the water side or the metal side or whatever you're talking about. So you just need that opposite relationship in terms of it. So again, if you're going to put all this together, you do need to have that negative sort of distributed through there. I really badly drawn our delta T. Here you can see that is the specific heat capacity. Like I said before, sometimes people will use C for that as well. All right, so why don't you try one here? A 110-gram sample of metal at 55 degrees takes the temperature of 150 milliliters of water from 23 degrees to 25.5. What is the specific heat capacity of the metal? Much like what we've been talking about, we have in terms of our metal here, we got a mass of 110 grams. We also have the temperature of it initially is 55.5 degrees Celsius. And it raises 150 milliliters, which is a volume of our water here when it goes for a swim in there. From initially 23 degrees Celsius to 25.5 degrees Celsius. And we're looking for what is the specific heat capacity here of our metal that went in there. So once again, here we know just out on the onset here, our metal was 55 degrees. Basically, our water was 23 degrees. So when that metal goes into the water, it is hotter, obviously, than the water. So we have our metal losing the energy or releasing the energy into the water in this case, which again is why we see the water's temperatures rise from where it started from, right? Because it's picking up all that energy, and that's what makes it go from 23 to 25 degrees Celsius. The other thing that we know for liquid water is the specific heat capacity that you always know. And in this case, we will use the ones with joules, since that's ultimately what we want to kind of end up with in terms of our units. We have everything we need here, really, for water to kind of do our calculation in terms of the water. If we take a look at our metal sort of calculation, if we keep it kind of separate, you could combo it together, but we could keep it separate as well. We're missing a couple of things. Clearly, we are missing the heat here that we can't figure out until we really figure out the water's sort of aspect. But we also know that in this case, our final temperature of our metal should end up being what? Should end up being the same as the waters, right? Again, because it's sitting in the water. So again, that's an important piece of information that we do have, which means our metal will eventually be 25.5 degrees Celsius. So when we go into our specific heat equation for our water, we will need the actual mass of it. So we have the volume, but we need the mass. So we remember that water's density, right, is 1 gram per milliliter. So we can always use the density of water, which again is a value you should know, to convert that into basically 150 milliliters times the density of water will give us basically 150 grams here of water in this case. As they cancel, I'm going to keep the same sig figs because I'm just converting it basically in this case. And again, the density of water could be 1.000, and so forth. So I'm not going to really look at it in terms of sig figs. Now I have everything I need for our water. We'll put that in there. We got 150 grams. We have our specific heat capacity of our water. And we have our final temperature of our water, 25.5 minus our initial 23 degrees Celsius. So I try to squeeze that in there. And that will get us for our water here. About 1,569 grams cancel, degrees Celsius over here, if it lets me do it, cancels, leaves us joules. Now, in terms of significant figures, once again, keeping track, this guy's got 4, this one's got 4. When we do the subtraction, we got like a 2.5, which is 2. Once again, really our answer here should end up right about there, about 1,600, I suppose. Again, I'm not going to round at this point until the end, but again, just kind of keeping track of it as I go through the rest of the calculation. We know that all that energy that the water gained had to come from the metal. So that is where we use our Q of the metal is equal to minus Q of the water. That means that the Q of the metal in this case will equal negative 1569 joules. Negative because it is exothermic for the metal. It's releasing that energy. Again, it should be the exact same value. So that's good because now we have our Q, and that's going to allow us to solve for S. Again, we're going to divide these guys to the other side, and that will give us that S is equal to Q of the metal divided by M and delta T. Taking our negative 1569 joules divided by our mass there for our metal in this case, which is 110 grams. And again, here we do want to go final minus initial for our metal. That's going to give us our important negative sign that we need to make the other guy become a positive. So we'll do that subtraction there. So that's going to get us here 1569 divided by 110. And I believe we get 30 when you do the subtraction. That will get us, I'll go this way, 0.4754545 joules, grams, degrees Celsius, as nothing cancels out. Now looking at sig figs, once again, we know this guy should be 2. This one is 4. When we subtract this, we get 30.0, I believe, which is actually 3. So once again, we should end up at 2 in this case, and that's going to take us to here. We do have to round up, so 0.48 joules per gram per degree Celsius. Any questions on that? So again, this is a very common way to figure out the heat and the energy in reactions. And essentially, like I said, all you need is a couple of coffee cups and a thermometer, and you really can figure out a lot of these sort of things. Any questions on that? So whenever you have anything where heat is transferred from one object to the next, you could use that sort of relationship. You could actually, again, once again, just to clarify, you know, you have your Q equals ms delta T, and your Q equals ms delta T, say once again for water or metal. These numbers here will be the same, except different signs. So you can set these guys equal to each other for the two things, like the water and the metal. But once again, as I mentioned before, you do have to have some type of negative sort of distribution on one of those sides to make sure you're going to add or subtract sort of correctly. So you got to make sure you distribute the negative at least to one of those sides to get that opposite relationship. And that will give you basically that kind of opposite relationship like we've been talking about. If you just simply set them equal to each other without the negative on one of the sides, you will add when you should subtract, you'll subtract when you should add. You'll get, kind of the wrong answer or stuff like that. Any questions on specific heat capacity? Okay. So we talked a little bit about last time as well that, there is another unit of calories, and it's sometimes a capital C, and that's referred to as a nutritional calorie. And one nutritional calorie is equal to 1 kilocalorie, which again is equal to 1,000 of the little calories, basically. A calorimeter is a device that is used, for example, to determine the number of calories there are in food. This is what is sometimes referred to as a bomb calorimeter, because essentially they're going to set whatever's on fire, whatever piece of food they put in there on fire. It's a super well insulated equipment where you have basically water and you have some type of thermometer that's in there. And basically you put your food item, like your chocolate chip cookie, I suppose. Got some oxygen, some ignition wires, and basically you set it on fire. Right? When you do that and you ignite it, as it's doing that, obviously it's going to give off heat and energy to the surrounding water. And because it's a well-insulated container, the only heat that water should pick up would be from basically the food that's burning. And frankly, you could just do a simple, like I said, calculation using the specific heat equation, because we do know the specific heat of liquid water. And you'll be able to figure out how much energy the water gained. That would then tell you how much energy was lost by the food item. And you could turn that from regular calories into nutritional calories. And that's how they get, some of those values that you see, for example, on food labels. When you look at food labels, there's basically 3 types of food that's on there: carbohydrates, fats, and proteins. And they all have what is referred to as a caloric value. So it's like 4 kilocalories per gram for carbs, and it's also 4 kilocalories per gram for basically protein, and it's like 9 kilocalories per gram for fat. And if you look at it like a nutrition label, they'll tell you this is how many grams of carbs there are, this is how many grams of protein there is, this is how many grams of fat there is. And you could actually do this. Remember, a kilocalorie is really a nutritional calorie. And you can figure out, again, how many calories you're getting supplied from fat, carbohydrates, and protein by doing that calculation. Again, just basically multiply them together. And all you would do is basically add up them all. And that's how they get, for example, the calories per serving that they put on the nutritional labels when you look at it. And again, it's done very similar. They can figure out how much energy and calories by doing a simple experiment like we just showed there, but this is how you get sort of that calculation. So, if you looked at any of those things, they typically would have, for example, if it said it had 5 grams of protein, it had 3 grams of carbs, and 4 grams of fat, for example. What you would do again is go, okay, 5 grams of protein, you would times it by the caloric value of protein, 4 kilocalories per gram. You would do the 3 grams of carbs, multiply it by the caloric value for carbs, and you would do your 4 grams of fat and multiply it by the kilocalories per gram of fat. And if you do all that good stuff there for top guy there, you get 36, you get 20, and you get 12. Add them all together. These are all kilocalories as the grams cancel. And you get all that together there. Your guy per serving has about 68 calories of whatever you were eating that had that sort of label. I would say in my experience, most of the time they do round down, obviously, in a lot of cases, that they get that like 100-calorie snack pack and stuff like that. So that's basically how you get those sort of values that you see on those nutrition labels. Now, constant pressure calorimetry is like what we're going to do today. And most of the time it is done under constant pressure. And like I said, basically a couple of styrofoam cups, a thermometer, some water is all you need. And you could do actually chemical reactions as well, as I mentioned. Again, because they are aqueous, they essentially are water based, and you could just assume, kind of specific heat of water. The way you could do this when you think about delta H, like, how hard is it to figure out the delta H of a reaction or to change an enthalpy of a reaction? It's not. You could actually do the reaction in the coffee cups. You could do your calculation using your specific heat equation. And at constant pressure, the delta H will equal Q, basically, at constant pressure. So very easily, even doing any type of chemical reactions, all you need is a coffee cup, some water, and a thermometer, and you basically can figure out the change in enthalpy or how much heat that particular reaction is going to be given off by just simply, again, following the change that's occurring with the water. Any questions on that there? All right, I kind of did that example. So here's an example, for example, of cereal. And again, same idea. You're just going to multiply the carbohydrates, the fats, and the proteins by the caloric value, add them together. And in this particular case, we had 2 servings. So, all right. To finish up talking about energy here, we're going to talk about what are known as thermochemical equations. And as I mentioned before, very commonly, the way that we see sort of energy given to us in equations is with the delta H. This is water going to water. The difference here is the states. This is ice going to liquid water, right? Basically, your ice cube melting. The delta H for that is 6.01 kilojoules per mole. This actually has a special name. This is actually known as the heat of fusion, which is the energy required to change a substance at its normal melting point from solid to liquid, not raise the temperature or anything like that, but just simply take it from solid to liquid or liquid back to solid just to do that transition. I think we talked about it earlier, but that does occur at the same temperature. So for water, that would be 0 degrees Celsius. So exactly at 0 degrees Celsius, we have the transition of water going from solid to liquid or liquid to solid. You have ice crystals sort of right at that point. It's not until you get a little above 0, below 0, that completely sort of transfers into the next phase. Now, what happens if we're looking, going the opposite way, taking it from liquid to solid? Again, the energy required to do that is the same, except that the sign is negative in this case. So it'd be negative 6.01 kilojoules per mole. That is because when we go from ice to liquid water, that is an endothermic process, right? So positive value. When we go from liquid back to solid, that is exothermic. Got to release that energy. That is a negative value. So one thing that happens when you have an equation, for example, is if you have an equation that is written like this, and say has a delta H of 100 kilojoules, but you actually need the equation written in the opposite direction, C plus D goes to A plus B. What happens with the delta H is the number stays the same, but the sign changes. So the sign changes here. And that's a very common sort of way that sometimes equations are manipulated. You may only be able to find the equation kind of going in one way, but you really are interested in what happens in the opposite direction. So how energy changes is basically the only thing that changes is the sign. If it's positive, it'll become negative. If it's negative, it'll become positive. That is because it's the basis of what we talked about earlier. When we calculate delta H, it's the delta H of our products minus the delta H of our reactants, which means if we reverse the reaction, our products become our reactants become our products. And that means you get the same difference, but the sign will change basically because those numbers will change as well. Another very common thing is maybe we don't need one of everybody, but maybe we need 2 of somebody. And we would have to, for example, say multiply this guy by 2. And that will give us 2 for our coefficients. By the way, these coefficients are sometimes referred to as the moles of each of these things. Yeah. What that does to the delta H is, in addition to multiplying the equation by a common number, you would need to multiply the delta H by a common number. And for that reaction, we would have 12 kilojoules of energy given off or absorbed in that particular case. So if you have an equation where you need to multiply the entire thing by 2 to give you 2a plus 2b goes to 2c plus 2d, then the delta H would also get multiplied by 2. And for that reaction, it would be 200 kilojoules basically per mole. By the way, if I started with the equation here on the right and I needed to divide everybody by 2, that would take me back to this equation, right? That will take me basically back to here. I would then divide this guy by 2, which would take me back to here. So if you have to multiply an equation by a common number, how that affects the delta H value is you would multiply the delta H value by that number. If you had to divide to get the coefficients in an equation to the right number by a common number, you would divide the delta H by a common number. So those are very common ways that you can manipulate these equations and sort of how the effect of delta H is. So again, if you reverse the reaction, switch everybody around, you change the sign of delta H. If you have to multiply by a common number, you multiply the delta H. And if you have to divide by a common number, you divide the delta H. Any questions on that there? Now, in addition to that, we can, for example, figure out things from an equation. So, for example, if we had, I don't know, we'll do, let's just say we have this equation. Obviously, we'll talk about balancing equations when we go back and talk about it in that chapter, but we'll do a little balancing here. Maybe we'll go like a 2 with 3. We'll go 7, 2, and we'll do all right, see how I did there. Make sure we have the same on everybody. We have 2 times 2 is 4 carbons. So 4 carbons, 4 carbons on that side. We have 2 times 6 is 12 hydrogens. 6 times 2 is 12 hydrogens. And 7 times 2 is 14 oxygens. That is 8 oxygens there and 6, which should be 14. So it is balanced. And again, we'll talk about how to do that and obviously in the appropriate chapter. Now, when we look at this reaction, for example, let's just say that this reaction gives us a delta H value of minus 125 kilojoules, right? So minus 125 kilojoules, right? A little bigger there. Okay. Now, let's say that in a reaction, we use only, say, 42 grams of C2H6, and we want to know how much energy would that basically release in this particular case. By the way, this reaction would be endothermic or exothermic. This reaction would be negative exothermic, yeah? So this reaction would be an exothermic reaction. This is a combustion reaction. That is ethane combusting and stuff. So when we look at this equation, and again, we're going to talk about some stuff right now that obviously the book assumes that maybe you know, because we did their chapters, which we haven't done yet. But when we look at the coefficients, which are these numbers that come in front in an equation, these are what I mentioned before, also sometimes referred to as the moles of each of these things. And we could actually come up with some conversion factors that involve the moles and the energy component that is here. So for example, we could say from this equation, for every 2 moles of C2H6, right? And again, that's where the 2 comes from right there. We get out in this reaction minus 125 kilojoules of energy, right? And because this is a conversion factor, we could use it the other way. Minus 125 kilojoules gives us 2 moles of C2H6. We could actually do this for anybody that's in this equation. So for example, if we're looking at oxygen, the coefficient in oxygen there is 7. So we could say for oxygen, for every 7 moles of O2, we also get out minus 125 kilojoules of energy, or minus 125 kilojoules of energy gives us 7 moles of oxygen. We could also do it for what's on the product side, for every 4 moles of CO2, we get produced, we release 125 kilojoules of energy, or for every 125 kilojoules of energy happens for every 4 moles of CO2 that's released. By the way, the abbreviation for moles is MOL. Yeah, that's the abbreviation for moles. So when we have this, if we want to know, for example, how much energy is going to be released when we do 42 grams of the substance, we can use the conversion factors here that obviously involves that guy. But much like every conversion factor, we do have to make sure things are in the right units, right? So our grams are in grams, but these guys are really in moles. And the one way that we convert grams to moles is to go to the periodic table, and we basically just add up all the parts. So if you go to carbon on the periodic table, you'll see that number on the bottom. It says 12.01. If you go to hydrogen on the periodic table, you'll see that number on the bottom. It's like 1.008 underneath it. These numbers here are what are referred to, and we'll talk more about this in a later chapter. These are what are referred to as the molar mass of each of these substances. And you could take that number off the periodic table, and you could say that this is 12.01 grams per mole, and that would be the molar mass of carbon. You could also say for hydrogen, 1.008 grams per mole would be the molar mass of hydrogen. We could use this as a conversion factor to convert this into moles, which is essentially what we need to do here. So to do that, we really just add up all the parts. So there's not just one carbon here, right? There are 2. So we do have to multiply this by 2. And there's not just one hydrogen, but there are 6 of them, right? The number goes to the guy to the left. So this number goes here, this guy goes to here. So we also have to multiply this by 6. So if I do that, this will give me a conversion factor that will allow me to get my number into moles. And that'll give me something like 30.07 grams per mole. And that would be the molar mass of C2H6, basically, adding it together. So we're going to use that as a conversion factor. Get rid of this since we don't need it. And if we take our 42.0 grams of C2H6, because this 30.07 grams per mole is a conversion factor, you could reuse it just like any conversion factor. You could flip it around. So just like normal, we want to go opposites to cancel. So since grams are up on top, we would actually need to use it like this. And that would be a mole of C2H6 is 30.07 grams. And if we do that, that'll give us 42 divided by 30.07. That'll give us something like 1.40 moles of C2H6. Any questions on that there? Now that we have it in moles, and again, the whole purpose of doing this is to get it to moles, we can now use our energy conversion factor. So 1.40 moles of C2H6. I want to get rid of moles of C2H6. That is going to mean I need to use this conversion factor. Gives me minus 125 kilojoules. 2 moles of C2H6. That's going to give me 1.4 times minus 125 divided by 2 minus 87.5 kilojoules of energy would be released in this particular case. It does make sense because basically when we look at the equation, there's how many moles of C2H6 in the equation? There are 2, and 2 moles will give you minus 125 kilojoules of energy. This time we're only using less than 2 moles, right? Like 1.4. So we're using less moles. We end up with less energy sort of being given off in this case. So you could do some calculations. And again, some of this is some chapters we haven't talked about. But you could use sort of the equation as a mole to energy relationship to figure out what's going on. So why don't you try one here? Why don't we do this one? And we'll just make it a little bit easier. 2A plus 4B, 3C. Let's say the delta H here, positive 325 kilojoules. So let's say how much energy is absorbed when 0.75 moles of C is produced. All right, I'll take the finding moles part out of it for you. All right, so based on that one, what do you get when we get 0.75 moles of C produced? So figure out the conversion factor you can get from the equation and figure out how much energy you would get from that. So I'm not going to focus in on everybody. I'm just going to focus in on C. And once again, this first number here, which is the coefficient, tells us how many moles of C that we have. And for every 3 moles of C that are produced, it tells us that basically we're going to get 325 kilojoules of energy. So we could use that as a conversion factor for every 3 moles of C. That's going to give us positive, in this case, 325 kilojoules of energy. Because it's a conversion factor, we could also, again, if necessary, flip it around and use it sort of in the other direction. We also know in this case that this is going to be a endothermic reaction, right? Because the delta H is a positive value. So we do know that this reaction, by the way, is endothermic, just based on that being positive. So in this case, unlike the previous example there, it's already in moles. So we're interested in not how much energy we would get if we made 3 moles of C, but we're interested in how much energy we would get if we made 0.75 moles of it. So we would just do a regular conversion here, 0.75 moles of C. We want to go opposites to cancel. That means we do need our C on the bottom there. So 3 moles of C, positive 325 kilojoules up on top. Those guys are going to cancel. And that's going to get you there. What we got there, 0.75 times 325 divided by 3 would be good as well. There we go. 81, we'll call it 81 kilojoules of energy, basically. Again, we can see it from the equation. If we made 3 of them, we get this much energy. Here we're starting with a lot less than 3 moles. We get obviously a lot less energy produced in that particular case. Any questions on that type of calculation there? All right, that wraps up chapter 10.